First of all, I would like to thank all the organizers for this wonderful conference and the wonderful place. So thank you very much, especially for Dominic. Thank you very much. Okay. So today I will give a, sorry. Okay. Okay. Doesn't work. Yeah. Okay. So today I will give a tutorial talk about Chiral Phonons and maybe just from the beginning and to the recent discovery about Chiral Phonons. So now, my research maybe 10, 15 years ago, I studied my main field is doing the thermal transport. So the thermal transport, is very important. Nowadays, just from here, this is a figure from the American Energy Department. They every year will give to the statistics on the energy consumption. So from here, we can see that 2/3 of energy are wasted in the thermal energy. So, and especially for the cheap heat dissipation, it also is a bottleneck in electronic technology development because of the heat dissipation. So the heat dissipation is a key bottleneck in the informational technology, and especially is of great significance for science and technology of information, energy, material, and environment. So how about for the carriers of thermal transport, we know that especially for the insulator, also for the semiconductor, the most important carrier is phonons. So the phonons exists widely in various physical phenomena, such as heat dissipation and thermoelectric effect, photothermal effect, electrophonon interaction, and even the superconductivity. Also related to the phonon. It's a relation to the electron-phonon interaction and Raman scattering. So the phonon particle, the quasi particle, is very important in the kinetic matter physics, maybe less important than electron. So after that, then maybe the phonon is the second important because the phonon can couple to all other particles. So such like the photon, electron, magnon, and the others. Okay, so we need to know the more physics about the phonons. Okay. For phonons, we know that it's a kind of collective excitation of lattice vibrations in kinetic matter. It's a typical boson quasi particles. Okay, so it's a lattice wave function. Okay, just we do the quantum. It's a quantum energy for the lattice vibrations. So from here, the phonons, this is a typical phonon dissipation of graphene. Okay, so here we know that to study the materials, we will check the phonon dissipation. Then we will found if there are no some negative parts, then this material will be solid and it's okay. Then we will do calculation further. But so for phonons, we only pay attention to the relationship of phonon frequency, momentum, dissipation relation, and scattering rates. For the thermal transport, we may need to know the group velocity of phonons for each mode. And for each mode, we will have to know the scattering rates. Especially in the materials with phonon nonlinear interaction with the higher order for phonons, like 3 order, third order, interaction of phonons. So from the nonlinear interaction, we can calculate the scattering rate for phonons and some lifetime for phonons. That's all. So for phone, so how about the phase effects of the phonon wave function. Is there any new physics in phonons? Okay. Okay. So now then after we do some thermal transport physics, then we move to the phonon Hall effect. Yeah. That the phonon Hall effect also is may related just in 2005. Yeah. Okay. That have an experiment. Then doing the paramagnetic materials, we apply a magnetic field. Then in the transverse direction, we will find a temperature difference. Yeah. How to explain this? Yeah. So here we just we do some theoretical work and to write the phonon, the Hamiltonians. Then we just for most of the people we also introduce the spin phonon interaction. Yeah. Just because like here, yeah, each atom will have some electron have a charge, then in the magnetic field we are affected by the magnetic field. So such kind of spin phonon interaction, okay? Yeah, each atom will have a magnetization. When the atom move around, then this like a spin orbital interaction. Yeah. So then this interaction will give the phonon Hamiltonian another terms, like here, these terms, okay? This term, like this U times P is angular momentum. This A, like the spin magnetization in each atom. So this they will give another interaction to this Hamiltonian for phonons. So for these phonons, so how to do this Hamiltonian, we can calculate the equation of motion for P and U, okay? So from here, we can write the equation of motions. Then we can get this wave function for combined together, this P and U, okay? Now this P mu and E is the eigenfunction of P and U. So in this wave picture, then we can write the effective Hamiltonian. So because of the spin phonon interaction, introduce this A into this Hamiltonian, then this effective Hamiltonian will be non-Hermitian. So nowadays, non-Hermitian is very popular in kinetic matter, just because they study the topological nature for this kind of Hamiltonian. So here, so how to solve such kind of Hamiltonians? We need some right eigenfunction and the left eigenfunction for this system. Then combine this together to calculate some Berry curvature, Berry connection. So here, so we from this Hamiltonian, then we can get some Berry curvature system. Yeah. Then and see here we can calculate the heat flux and can write some heat flux in this form. Here it's consistent with the electron case. Here this is a diagonal term. This is off diagonal term. Diagonal term is just like the transparent, the transport current. But here is the this is like the longitudinal terms. But here, this Berry curvature terms will introduce a transverse term to affect the heat current to move, turn around the heat current. Okay, so here then we can to calculate the Berry curvature in this and write some the thermal the Hall conductivity, and we can also calculate some chain numbers for each phonon modes. And these chain numbers have changed at some point, then give a phase transition to the thermal Hall conductivity. So here this work, but not perfect. Then I will talk later, because in this heat current term, we need to consider another just spin terms. That self-turn around terms will contribute, will affect the transport term. We need to delete that. Okay, so but here this work is very just very earlier work for topological phonons. Yeah, so after that, but we first time to detect the topological nature for phonon. Okay. Here, so but here this topological phase term, physics, we can just generalize from phonon to magnons. So nowadays, because phonon and magnon can interact each other. So when we do phonons, we also need to consider the magnons. And some picture we can generalize. So here we can generalize the topological phonons to topological magnons. But for magnon, it's very easy and more easier. Just we calculate the Berry phase, for this Berry connection. So but here, this Hamiltonian is more easier than phonons. For phonon, we have non-Hermitian term, but here it's all in the second quantization and no non-Hermitian terms. So then we just give some terminology for topological magnon insulator, but it's just a conceptual terminology. But because the phonon magnon is similar, is the same with phonons, they have no Fermi level. Okay, so then for all these phonon and the magnon cases, there are no insulator such kind of terms. But here, if we for this system, we have some band gap. Okay, if we use some waveguide, we can to just cancel all other modes in the band. Okay, but only left the modes in the band gap transport. Then because there's the edge mode in the band gap, then this mode can be topologically protected. Okay, then we can call this topological magnon insulator. But I think because this is not so important, just from the conceptual terms. Okay. So this because all we do the phonons, the magnons, then can we combine all these particles in a unified picture? Okay. So here can use the semi-classical systems. We calculate the self-rotation and edge part. Then we can combine all these quantum particles in one picture. Okay, so here in the end, we can write some Hall effect, this Hall, thermal Hall conductivity. Then for the electron, phonon, magnon, all this picture can combine in one formula. So from this one formula, we can get the phonon, magnon, electron, all this thermal Hall effect can in this, because all these are wave picture. Okay, so for all these wave pictures, they can just include in one the semi-classical wave picture. Okay, using this edge self-rotation and edge terms. Then in the total current, we just cancel this, get to the transport current. From this transport current, then we can get this Hall conductivity. Okay, then get the final formula. Okay. So here maybe all this I talk about maybe have no relation with chiral phonons. Then we will go forward. Okay. Okay. So this just very recent to some topological value magnons. It's just similar to the topological electron cases. We can find some topological practice edge modes, or some, if you break time reversal symmetry and inversion symmetry, then we can get some one edge transport in some in nanoribbons. Okay, so no new physics. Okay, and now if this system then no time reversal symmetry broken, then if we apply some temperature difference, then we can get some nonlinear phonon Hall effects. Okay, so in this system there are no magnetic field, no magnetism. But if because it's similar to the 2018 PIL paper, they have some in time temperature gradient induced phonon angular momentum. It's similar. Okay, so the phonon angular momentum we will talk later. It's related to the phonon Hall effect. Is similar picture. Okay. Okay, so here we already introduced this the phonon will affected by magnetic field. Okay, under the magnetic field, the phonon can be turned around. Okay, then that is the phonon current not only transported longitudinally. Then if in applied magnetic field in the perpendicular to the plane, the phonon can be turned around just because the spin phonon interaction. Okay, and we will ask some more ways. So in this picture, how about the phonon angular momentum? Okay, is there any phonon angular momentum? Yeah, because it's very is similar to the electron cases. When electron case, when applied magnetic field, the electron when have a Lorentz force, then will turn around. Okay, the electron will get angular momentum. So how about the phonons? Yeah. So whether the phonon can have angular momentum. So this phonon angular momentum can relate it to the very old problem. Which kind of old problem is the Einstein-Dehaas effect? Yeah, Einstein-Dehaas effect just in 1918s. They just tried to prove the ampere molecular current. Yeah, when for the magnetic system, when we apply the turn on, then this system will have a magnetic field. But so when the magnetic field magnetization, then electron will be when turned around. Okay, so the electron will get the angular momentum. But the whole system, the conservation will have a conservation for angular momentum. So the original momentum is 0 angular momentum. Well, but now the electron have an angular momentum. So the system, the cylinder system will have another angular momentum when turned back. Okay, so Einstein and Dehaas, they do experiment and to measure, and then when they publish the result, they get, when they do experiment, have two results, okay, 1.45 and 1.0. So from the idea of Einstein, because this result should be 1, because from his calculation, he has done this relation, then the G factor should be 1. But need a publication. So we need to discard other results because these results are not consistent with the idea. So just discard this. Yeah, but yeah, subsequently there's some experiment. This G factor is almost 2. Why this? Because in the original idea, they didn't consider the spin angular momentum for electron, only consider orbital angular momentum for electron cases. So just because the data discarding, then they didn't find the spin. Okay, but subsequent experiment they prove this. We need to consider the spin angular momentum for electron. Okay, so here, so we will ask further question. In this system, the electron have spin angular momentum, have orbital angular momentum, and the cylinder, the crystal, have angular momentum. So how about the atom vibration? Okay, how about the phonon? On the phonon only they vibrate in the equilibrium. Okay, so how about the phonon? Whether this phonon can have non-zero phonon angular momentum? Okay, yet we just check. Yeah. This system for here, so spin case is spin orbital for electrons. So for lattice part, we will have spin, the total angular momentum with conservation. So this we do measure because after magnetic field, then all electrons will spin in along one direction, and also the electron have orbital angular momentum. So the lattice system will have opposite angular momentum equal to here. So here this, then how about the phonons? Yes, yeah, just atom the nearby the equilibrium case, whether the phonon have 0 or non-zero angular momentum. Okay, so from the angular momentum we can get the definition. Here we already doing mass normalized. We didn't consider because that mass can be absorbed in this. The formula is very trivial. Okay, so here just for these two is equilibrium coordinate for each atom. Okay, so this time together is we call the lattice or the cylinder. Okay, angular momentum. So how about the other terms? This u times u dot. So whether this angular momentum is 0 or not. Okay, but in the from the naive idea, this because the u average for the u or u dot is 0, then time together whether this is 0 or not. Yes. Okay. So we do the calculation. From that we define here with just from u time clock with u dot. Then we use second quantization for u. Then we do after very short derivation. Okay, not so difficult. Okay, then we can get in equilibrium. We get a Phonon angular momentum in these forms. Each mode will have an angular momentum in this. And from this formula, it's easy. When we do the limitation, go to the limit time T temperature equal to 0, then this Phonon angular momentum still there. This is 0 point, similar to 0 point energy. Now is a 0 point angular momentum. For the magnetic system, we will consider have a 0 point angular momentum for phonons. Okay, so for then here, but we will go back to the Phonon Hall system. Okay, for the Phonon Hall system, this spin phonon interaction will break time reversal symmetry. Then this angular momentum for k and minus k, they will not do, is not an order function. Then they cannot cancel each other. Then we will get a non-zero Phonon angular momentum. But for some trivial system without spin phonon interaction, this is a harmonic system. This L k and L minus k, they always cancel each other. Okay, so this total angular momentum will be 0. Okay, so now, we then calculate each mode. Then we can get for each mode have an angular momentum. Then we can calculate the total angular momentum. For total angular momentum, it is related to the temperature. When the temperature is high enough to go to the thermal limit, okay, so then this angular momentum will go to 0 because the phonon is a completed basis for phonon picture. Then we'll cancel each other. But when the temperature go to 0, the angular momentum will be larger. Then we give a proposal for how to measurement the experiment, the angular momentum. We just change the temperature. Okay, when the temperature change, the total angular momentum will change. Because this is a magnetic system, when change magnetic field or change temperature, magnon case will also change. Then if we change the temperature lower than the Curie temperature, then for magnons, the angular momentum almost no change. Okay, then the change comes from the phonon case. So, but this experiment is not so easy to do. Okay? Only after maybe you all know, just very recently, they had to find the polarized phonon carries angular momentum in the ultra-fast demagnetization. This experiment is the reverse experiment for Einstein-Hasse effect. Okay, for Einstein-Hasse effect, you apply magnetic field. Then for electron, under this every atom will get every electron get angular momentum. Then the whole system, because they will keep the conservation for angular momentum, will move back, have a backward angular momentum. But here for the demagnetization system, when you to have a less input to the system, the magnetization will disappear very quickly. So, but when magnetization disappears, the angular momentum will how does it go? Okay, but from the naive point of view, then we will find the backward rotation of the system, but they didn't. We never find this. So whether the angular momentum will come away, yeah, whether. So we just lost it in a long time. Then now, only recently they use the electron spectrum. They see each atom will do a round just locally at each atoms. So this is similar related to the Phonon angular momentum. But this experiment is not a direct measurement for Phonon. Okay, yeah, we maybe is there any we can prove this? Yeah, this. Just according to our PRL papers, yeah, only recently, yeah, this one paper we already accepted by Nature Physics. They do the experiment to measure the Phonon angular momentum. They just change the temperature. Yeah, they found, yeah, when temperature changes, the angular momentum, yeah, will change. This, yeah, to all these other effects you just already considered. We found that the angular momentum is come from the phonons. It's a direct experiment. Okay. Okay. So here is just we do the phonon angular momentum. Okay. So for phonon angular momentum, each mode, but that means for this phonon angular momentum, we also consider this. The whole systems, we just to detect the total angular momentum for whole system. We didn't care about the angular momentum for each mode. Okay, so we detect this, and because the total angular momentum, since we already analyze the angular momentum, the formulation, yeah, just because the time reversal symmetry is broken, then the total angular momentum will come out. Okay, so we go back to the angular momentum, the form. When do the time reversal, the symmetry, when to operator, yeah, we do this, then time reversal, then the angular momentum is an odd function, because from this angular momentum r times p. P is equal to dr dt. Okay, when you transfer to the sign for t is time. Okay, when you transfer the sign of t, then this whole formula will give a negative sign. Okay, so here we get this odd function for k. Okay, k is the momentum part. Okay, so when you do the spatial inversion, yes, the operator, then this r. Yeah, when r, because r times dr dt, okay, when r change sign from positive to negative, then this sign will keep the same, okay, will not change. So when the system have time reversal symmetry and the spatial inversion symmetry, then this function will be odd function, also be even function, so must be 0. Okay, so we need to break one of the symmetry, time reversal or inversion symmetry. So for for the small Hall case, yeah, just for by introducing spin Phonon interaction is a small Hall case, because the time reversal symmetry is broken, then the total and the angular momentum will not be odd function. That is for the angular momentum in k and the minus k, they will not cancel each other. Then the total angular momentum will be non-zero. Okay, but so here this system, when we publish the paper for angular momentum, but still others some criticize this because the angular momentum is very small and it's not easy to detect. It's very difficult to detect. So we just think about, is there any other kind of cases for the phonon have non-zero angular momentum, or for each mode, yeah, whether this a single mode have some non-zero angular momentum or not, then we need to break the spatial inverse symmetry. Okay, so the spatial inverse symmetry we just can use this very small, very easy model for the still the graphene or just the boron nitride model. Okay, then here these atoms are not equal. Then this inversion symmetry is broken. So how about the phonon modes? Then we go to the Chiral phonon. Okay, now this each we find. So how about whether the Chiral phonon is important or not? Yeah, we related to another field, electronics. They do just electron scattering in the electronics. Still, they also have a C3 symmetry. Okay, so it's like TMD material. Okay, or boron nitride material. They also have this K and minus K, and K and minus K. They when do the we use electron scattering in one valley or in one band. Okay, for one valley, when electron from the valley band to the conduction band, okay, then this the momentum will change. So this angular momentum change will related to some chirality of the photons. Okay, so because the energy change and the angular momentum will change, but the momentum will not change. Okay, but if the electron scattering from one valley to another valley, now the momentum will change a lot. Okay, the momentum change a lot, but the photon cannot have such large momentums. So in this case, the phonon will come into this process. Now, maybe not necessary. We will have some defect. Okay, some defect case also can change the momentum. But many cases, the phonon will evolve into the electron inter-valley scattering. Okay, so how about the selection rules for these phonons? Yeah, because in one valley, we will introduce the angular momentum and some definite angular momentum for photon. So for the inter-valley cases, how about the phonons? Whether the phonon can also have some special angular momentum. Then this will go to our Chiral phonons. Okay, so move to the Chiral phonon. Yes, then we calculated the very easy model. Boron nitride. Also this model we calculated the phonon. The angle functions. Because in the textbooks we only focus on the gamma point. Long wave limit cases. We check the wave function. Then we get some acoustic model or some optical mode. For acoustic mode, all the atom will move along one direction. Okay, so we have some LA, TA, ZA, or some LO, TO, or ZO. Okay, but all these modes are linear polarized, just in the long wave limit. But so if we go away from this gamma point, we go to the K point, we check this wave function, we will find this mode will be, we are doing some circular movement. Okay, we are not linear polarized, we'll be doing some sphere. Okay, or some cases, if between these 2 points we are elliptical, not which circle, not circle, will be some elliptical cases. Okay, so how about this phonon? But maybe after our paper, some guys say this is just the phonon will have angular momentum. So why we call this Chiral? Okay, maybe this is not a real Chiral. It's false Chiral. But because for the two-dimensional cases, when we calculate the receptacle lattices, we already have some some the solid the direction there. We need to define a k. Okay, then in this z direction, then we can calculate some reciprocal lattice along kx, ky. So if we have this k direction, then we can define this kind of the motion to this. If this angular momentum is in the same direction with this k, this we can call this right circular. Okay, if this angular momentum is negative to the k direction, then will be left. Okay, so we still can get some kind of call this some Chiral Phonons. Okay, but not strictly terminology. Okay, but it's we call this is all these phonons will have angular momentums. Yeah. Okay, so for these phonons, we can, from another point of view, to get this Chiral Phonon or some the phonon with polarization. Now, we just similar to the photon cases, we can define another basis for each atoms. Each atom can do some right circular or left circular. If in this basis, we can rewrite the phonon eigenfunction, each phonon wave functions in this basis. So for this basis, then we can get the polarization for phonons. Okay, this polarization is exactly the same with the angular momentum we defined before. Okay, yeah, this definition, this calculation is just from the definition for angular momentum. Yeah, we calculate this, then write each mode is in this form, and from this point of view, we also get this the polarization for phonons is exactly the same. So that means, yeah, each phonon mode will have an angular momentum. Then for the system with time reversal symmetry broken, then this will have non-zero. Okay. Now for the system without time reversal symmetry, but we can look at for each mode. Look at each mode. Okay, so now then we can to calculate the polarization for each mode and each sublattice, and the total the polarization will combine together. Then if we have some ionic, each mode, each atom, if have some Bohr effective charge, okay, then we'll have magnetizations. Yeah, because you look at the mode here, just one, okay, one atom doing rotation, then we'll have magnetizations if this have a charge. Okay, for this, even for this mode, because these two atoms doing opposite rotations, so there when you have opposite charges, then this mode will give a large magnetizations, because from electron change doing circular, then we'll get a magnetization. Okay, so here for each, when we excite one of the mode, then this kind of mode will get some magnetic field. Okay, magnetization. Okay, so here, so already in this paper we're doing some calculation for the magnetic mode. Okay. Okay, so for some special mode like this way. Okay, doing this way. It's not a traditional case doing some linear polarization. For this kind of angular mode, atoms just doing opposite circular movement. Okay, okay. So, but for this, just every atom is doing the circular polarization mode. But for this total mode, how about the symmetry for this mode? When we do the threefold rotation, this will get some pseudo angular momentum for this mode. Okay, because when we operate this threefold rotation, then go to this, because here have two parts. Okay, you have this hanging part and some orbital part, because in each atom we do have some mode part, and also because the different atom will have a phase change. Okay, so here when do this operator, then for this part we call this spin part pseudo angular momentum. For orbital part we'll also have a angular momentum. Okay, so then yeah, for some these cases we can calculate the total phonon pseudo angular momentum equal to spin part and open part. But because this AB lattice is the partial function for the phonons, so their pseudo angular momentum must be the same, because they will have the same phase change for the whole wave functions. So we can get the phonon pseudo angular momentum. Okay. Okay. So here when we do, we go back to the introduction, how the phonons evolve in the electron intervalley scattering. Okay. So here when we inject a electron go to the conduction band, for the valence band, then we when the Hall go to another places, in the Hall process, then we need to consider the photon energy, electron energy, and the phonon energy, momentum, and angular momentum, because all these three elements will have a conservation. Okay, so conservation for energy, conservation for momentum, and conservation for pseudo angular momentum. So we need, so we can do experiment and to analyze some kind of phonon will evolve in this system. Okay, so now another if we can inject some special phonon come out. Okay, for different phonons will have different barrier coefficient. Okay, for left on the right, the phonon, they have different barrier coefficients. So if you have some strain gradient applied to the phonons, this will like some magnetic field when turn around the chiral phonon move different ways. So one kind of phonon will go to left, another kind of phonon will go to right. This we call this some value phonon Hall effect, but it's just a theoretical proposal. But so far haven't been observed. Okay, in the systems. If we can inject some special phonons, then in this system if we can apply some strain gradient. Okay, I don't know how to do experiment. Okay, but from theoretical point, may have some value phonon Hall effect. Okay, it's similar to the value electron cases. Okay, okay, so yeah, then we can go to this is ZHANG do the experiment to verify our chiral phonons is exactly the same with our PRL papers. Yeah, just the same cases. You need to consider energy conservation, momentum conservation, and pseudo angular momentum conservation. Exactly the same. Okay. Okay. So we'll go to very quickly to some other cases. Frequency adjustable non-degenerate chiral phonons. Yeah, because for the graphene cases, because the atom the reversal inversion symmetry does not break. So how to break the inversion symmetry? We can put some boron nitride, yeah, to this graphene, because their lattice mismatch not so large. Yeah, they can put together. So because the interlayer interaction will break the inversion symmetry, then we can get some chiral phonons. It's non-degenerate. Yeah, and when we to adjust the pressure, then this chiral phonons, the gap will change. It's very trivial, not so. Then and for elliptically polarized chiral phonons, but so far this is also another theoretic works because we made most of the papers just doing the Bohr-Nachard model, okay, or some TMD materials. We just check the chiral phonons. So how about this Kagome lattice? This Kagome lattice is very popular in magnetic systems because such kind of system have a DM interaction. Okay, this is a pure core that how to speak that lattice along 111 direction. Along 111 direction we will have the Kagome lattice. So just in this lattice have DM interaction. This DM interaction is similar to the Lorentz force to the magnon. Then the magnon will go turn around. It will have a magnon Hall effect. Okay. Then just because that the DM interaction will get introduce some barrier curvature to the magnons. Then we'll have some magnon Hall effect or some scamion some cases. So all these cases is doing that Kagome lattice. So we just calculate the phonon for the Kagome lattice. Yeah, it's very interesting. So now the phonon case is not doing circular. Okay, it also some elliptical local variations. But all these modes have C3 rotation symmetry. Okay, also have some pseudo angular momentum. Okay, yeah, we just do some calculation. So for different cases, the angular mode will be different, but the conservation law is the same. Okay, but so for here, this system also have pseudo angular conservation because the symmetry. Okay, then yeah, just we can for some indirect band gap, we can just inject some electron scattering just one time. Because for the science paper, we need to inject the photon to scatter the electron in one valley. Then the Hall will go to another valley. Yeah, have two processes. So for the indirect band gap, maybe we can just one step can inject this. Okay, in this Hall process, then this energy, momentum, angular momentum conservation in this one-step procession. Okay, so yes, and dark excitons brightened by chiral phonons. Yeah, just because previously we don't know whether the photon has pseudo angular momentum, then some process maybe will not happen. But now because the photon have angular momentum, can happen in this inter-valley scattering system. Okay, so in tandem, here this system is we can inject, have a linear photon come in. Then because each linear photons can be combined by some left and right photons together. For different kind of photons, we will inject different correlated phonons. So for linear cases, we will have left and right phonon and left and right photon. They will entangle together, have a chiral phonon and photon entanglement. Yeah, and we just all that because now the phonon will have another degree of freedom. Yeah, have a correlated down left or right. So maybe we can use this degree of freedom to transport the information. But if we need this transport, need some group velocity, okay, for phonon, then we go to the three-dimensional cases. Along high symmetry lines, the chiral phonons will have group velocity. Okay, so now if we can inject some one chiral, this is real chiral phonons. Okay, now this chiral phonons will just go along some high symmetry lines. Yeah, so different chirality, then they can go along the same high symmetry lines. So this work just get you. We can get the chiral phonons in 3D cases where if this in every layer of this have some inversion symmetry broken, then we can get chiral phonon with group velocity. But now here the chiral phonons they is degenerate. They both left and the right chiral phonons can go through one symmetry lines. So whether can we decouple this? Yeah, for different chirality phonons, we'll have different group velocity. Then we can make a special chiral phonon along one special direction. Then we go to another work. For this chiral phonon diode in chiral materials. For the chiral materials, then now the different chiral phonons will have different group velocity. So for here, it's a positive group velocity have is a right circular right chiral phonons. That means if we inject a photon here, then the chiral phonon is created. This chiral phonon can transport along this direction. But for this is right chiral phonon. For the left chiral phonons, they cannot go. Okay? Because if we use another photon inject, then we can create the left chiral phonon. But this left chiral phonon cannot go through along this direction. Okay? We need to transfer to another material. Okay, for left. Okay. So here now we can decouple the chiral phonons. We can use the definite chiral phonons transport along some definite directions. Okay, this we call this a chiral phonon diode. Can only transport along one direction, but backward cannot go backward for this right cases. Only in the opposite chirality phonons can go backward. Okay, so this very interesting. Now this for some chiral, because for the chiral material is very is popular in the bio system. Okay, biomedical systems. So now with this chiral phonon can relate it to life science. Okay, because for different chirality material or different chirality medicine, we have different action to human body. But so because if we test some material, sometimes maybe we need use the phonon to coupling. So maybe these chiral phonons can transport along one definite direction. Another chirality cannot couple together. Then we can get some information for these chiral materials. So this is like the, okay. So chiral phonon matter to MTMD. So I almost run the time. Okay. Okay, or go fast. Okay, chiral phonon, then activate the spin feedback just because we have temperature difference, then can have magnetizations. This magnetization can affect the electron transport. Okay, this observation CPAS effect. And nowadays, we also do some trial on the chiral phonon to an electron coupling. Then we introduce another coupling for chiral phonon electron cases. This is well for toming, okay, for all the coupling. This for is a special coupling of chiral phonon and electrons. This electron interaction can also mediate high temperature superconductivity. Because nowadays the superconductivity is a very difficult problem. Okay, we don't know what's the mechanism. Maybe can relate it to high chiral phonons in the future. We just do some trial. Okay.
What is the order parameter of this?
Then just you introduce this electron chiral phonon in the some S wave maybe. This kind. Now this is just very primitive works. But we introduce this kind of interactions. Because why we only can consider 3-order interaction? Because in the phonon cases, nowadays the 4th order coupling is very important for thermal transport. Okay, so here we can say that maybe this can affect superconductivity, and we can use this chiral phonons to do some Chiral Phonon device. Yeah, sometimes 1 + 1 equals some 3 other cases. We just do some trial. Yeah, ideal conception to use these Chiral Phonons to transport some information. Okay. Okay. So now this Chiral Phonon will become hot. Every year we have more than 200 papers. Okay. So can go to our conclusion. Topological phonon, we just from topological phonons. Now and then we'll go to phonon angular momentum to Chiral Phonons. Yeah. Okay. So maybe in the future still a lot of work to be done. Okay. That's all. In the end, we'll have a group and maybe long-term recruitment. If you are interested to work in China, nowadays it's also comparable. Okay. 1 million RMB salary. Okay, so welcome to China working. Okay, thank you very much.